practical, looking at the effect of surface area on rate of reaction. So that worksheet we'll work through, we'll finish up, we'll write up, we'll answer questions on it. But I'm going to do the theory bit with you here and now. So to start with, we're just going to talk about what we mean by surface area and how we think that affects rate of reaction. Okay, so last time we talked about previous lessons we talked about what we mean by rate of reaction. So rate of reaction is equal to the change, in this case, of volume divided by the time. The change of volume we had in centimeters cubed in this reaction, and time is in seconds. So the rate is in centimeters cubed per second. Per just means divided by, doesn't it? So rate in centimeters cubed per second for the reaction you just did was in centimeters cubed per second. And we looked at the effect of small marble chips and large marble chips in the reaction between calcium carbonate and acid. Now, we haven't done the acids topic yet, but we'll learn, as you have done in Key Stage 3, that metal carbonates react with acids to give salt plus water plus carbon dioxide. And the great thing about this reaction from our point of view now is that carbon dioxide is generated, which is a gas, and we can measure the production of that over time, either using a gas syringe or, as you guys did today, using an inverted measuring cylinder filled with water. Right, so we can measure it in a couple of different ways: gas syringe or inverted measuring cylinder with water. It's worth being able to just sketch that. So I'm going to draw a bad effort at sketching that now, and you can have a crack at copying it. So it's quite small. So you had a measuring cylinder which contained marble chips, a delivery tube that came through a bung, and that bung found its way, or the carbon dioxide passed through the bung, through the delivery tube, into an inverted measuring cylinder that was filled with water, and we could measure production of gas over every 20 seconds or so, because we could look at the values, the numbers on the inverted measuring cylinder. So the inverted cylinder filled with water inside a trough of water. It's going to say trough, and that's how we did that experiment. Not to scale that picture, is it? Never mind. So what's going on? So what you found, I think, from what you were telling me as I was wandering around, the small marble chips reacted faster, right? Is that what we all saw? I think more or less people found that. And your graph, when you draw the graphs, which we haven't done yet, your graphs will probably look something, or one of them might look like that. Will the smaller marble chips be steeper or shallower? Did you shout it out? Steeper. Yeah, steeper. The small marble chips will be steeper. It might end up looking something like that when we've finished. Okay, so the volume versus time. So small, large. But what we've got to be able to do is know exactly how to sort of write this up in our exams. Okay, so what you would first of all say, and what people often miss out, is the actual outcome of the experiment, or the expected outcome from the information given. So stating that small marble chips reacted faster is often worthy of a mark. Now, it's sometimes so obvious to you guys because you're very clever, you don't bother to say the most easy thing. So small marble chips reacting faster than the large marble chips can be worthy of credit. But we've got to think about why that is. I'm just going to pause the video for a sec, give you a chance to have a little chat and some of you to catch up writing. What's the reason for that? Let's see what level your answers are at right now based on your Key Stage 3 knowledge. In the discussion we just had, people were talking about the fact that the marble chips were chopped up smaller, and so they'd react faster, which is true, but not that much detail there. People are also saying, talking about surface area to volume ratio. We don't want to talk about surface area to volume ratio. That's really important in biology and physics. This idea that heat loss is faster with things with greater surface area to volume ratio. This is simply about amount or number of exposed particles to the acid. It's all about surface area, and that's what we're going to talk about from now on. Okay, so small marble chips reacted faster because they have, this is really easy, right? But they have a greater surface area. And you might be asked to calculate the surface area of something, or even calculate the surface area to volume ratio of something. I've seen that in exams. So can you do that basic maths? We're not going to do that now, actually. All I'll do is remind you how to calculate surface area, which is to work out the area of one face. Let's say this was a 2 centimetre cube. The area is 2 centimetres, times 2 centimetres, which is 4 centimetres squared, and you times that by the number of faces, right? So it's 4 times 6 equals 24. But we'll spend some time practicing the maths you might need, squared, later on. Right, so small marble chips, you chop them up into little pieces, they've got a greater surface area. Let's have a look at what that might look like. So you take a big block like this, and the only exposed surface there is what you can see on the outside. But if you chop that up into a number of smaller blocks of the same mass, you have lots more particles on the outside. So I'm just going to chop that up like so. There's, just imagine they're the same mass as each other, but it's got so much more surface exposed. And what we talked about last lesson is we started talking about the C word, right? It's all about the word collision, because chemical reactions only happen if chemical A and chemical B bump into each other. Or the word we use in chemistry is collide. This is collision theory. And in fact, collisions have to happen in such a way that the collision's happening at the right angle, with enough energy and all that kind of stuff. But for today, we're just going to focus on how often those collisions happen, or how frequently they occur. How many happen per second. So I'll talk a lot, as I've said already, about the F word and the C word in this topic. F word being frequency, in other words, number per second, of collisions. That's the C word, all right? So if you've got a greater surface area, what we have to say in our exams to get a mark, and this is the mark that's most often lost, so I'll double star this for you: more exposed solid particles, right? There are more particles of the calcium carbonate, the solid, that's exposed to the acid we're reacting it with. I probably should have put up here the state symbols, making it clear that calcium carbonate is a solid, the acid and the calcium chloride are dissolved in water, aqueous, and water is a liquid. The key thing there is that the calcium carbonate is a solid. This only applies to solids, of course. And we'll look at other examples of this next lesson too. Now that means, and as you'll say for a lot of these explanations, there are more frequent collisions. There we go. And that is really all you've got to be able to say for this. So more exposed particles to the acid, so there's more frequent collisions between the reactants. You could add to it if you want to. If there's more frequent collisions, the reaction is just going to be faster, right? They're going to collide more often. Right, so I'm going to pause there for a sec. So you've got some data here. So hopefully your data looks something like this. So for those not with us today, if you can make out this writing, that's the sort of data you'll have had for these. So the larger marble chips took longer to get to 100 centimetre cubes of gas produced, and the very small marble chips, they produced the gas much more quickly. The reaction was faster. And so we've proven this worked. And so I want you to plot that data on the graph paper supplied in the pack there. You can work on that now, and then there's some questions underneath which you can get on with. Right. So on this graph here, the plotting has been done perfectly, and the graph axes have been labelled. Though we must remember to put units for whatever we've measured on the axes. Okay, and clearly one graph is steeper than the other. This one here is it must be the small marble chips, and up here this graph, this line here is the large chips, and we know that because it's a slower reaction, therefore a shallower gradient. but they end up at the same point. They end up producing the same amount of gas in the end, okay? And that's important, and a point we'll come back to later on. But there's a slight issue with the graphs in that these were drawn with a kind of join the dots mentality. And that's very common, but also won't be given a mark. And what we need to do is to draw the best curve we can with the data that's there. And that's often really difficult to get right with imperfect, with normal data. That's quite difficult to get right. So I would say, if I'm going to draw this bottom of these two graphs with the large marble chips, I would say the first part of that graph is basically linear. So can you see that's a wavy line there? We're never going to have wavy lines. Graphs are meant to represent the general trend of what's going on. So either it's going to be a straight line or a smooth curve. This to me looks like it's going at a roughly straight line to start with, and then curving away as the reaction tails off. The reason why there's a kink here is because, remember, right at the start of the reaction, you put the marble chips in, and then there was a gap and you put the lid on. It might be things like that, and so when you shove the lid in, that causes a load of bubbles to bubble in through to the measuring cylinder. So you end up getting slightly erroneous data. So I'd say this here is probably a slight anomaly. We'll be looking out for things like that. So I'd say this data from there on is pretty good. And so I'd probably be tempted to draw a line through that data there and then curl away as this graph does, like that. So that's the kind of thing I'll be looking for. And the other graph is much better. I'd probably say it's much more like this though. So if you can make your graphs look like one smooth line, that's much, much better. The purpose of graphs, folks, eyes this way please. Folks, eyes this way please. The purpose of graphs is that you can do interpolations from them. In other words, you can read off them what would have happened at time points you weren't able to measure. So what would the volume have been at 30 seconds? Well, I can use the graph to figure that out. Because if you're following a wavy line, you're being pulled away by the error data that's on there, the anomaly that's on there. So hopefully that's helpful to you. At the moment we're still practicing. There'll be plenty more opportunity to draw up graph data. At the bottom of that page there's some, on the following page there's a couple of questions there. Can you have a look at the questions over the page, read what it says at the top here, and tackle those questions A, B, C and D, and that will keep us going for the last 5 minutes or so of the lesson. Thank you.